Well, thank you everyone for coming. I appreciate you coming out and joining this session. I'm Kyle Story. I'm a computer vision engineer at Descartes Labs, and today I want to tell you about how computers see Earth, a machine learning approach to understanding satellite imagery at scale. And so there's a few things that I'm hoping, depending where you're coming to this talk from, that you might take away. First, I'm hoping that everybody will understand how we've been able to build a platform within the Google Cloud, how that's allowed us to provide an efficient development environment for building machine learning models, and then scale those models across large data sets to be able to understand the entire globe. Second, I'm hoping that you will take away the types of problems that we've found compelling and that we've been able to address using satellite imagery and machine learning techniques. And then third, hopefully get you thinking about the types of problems that you might be able to address with these data, with this type of infrastructure, and how you might be able to address some of your business problems, whether that's monitoring infrastructure, supply chains, agriculture, even understanding the natural ecosystem. So the world is teeming with activity, whether that's man-made infrastructure, like here in the zoom-in, a sports stadium inside of a city, or that's agriculture, shown here with crop circles in South America, or the natural ecosystem. There are things happening all over the entire globe all the time. And satellite imagery is a particularly effective way of being able to zoom in and understand what is going on all across the globe. So there's a big dynamic range in what we want to be able to understand. We want to zoom all the way in to the human scale of a few meters or a meter or less. And then we simultaneously want to be able to extend these analyses across countries and continents. So it presents a big challenge. In satellite imagery, we are at the beginning of what we think as a regime change in simply just the data set. So previously, satellites were big and expensive, costing of order $100 million, weighing a ton. Companies and governments could only send up a few of these at a time. And so while these satellites provide excellent and incredible information, you can't monitor the entire globe with any sort of regular cadence. With the advent of CubeSats and smaller satellites, that's really changing. So now companies are able to build satellites for $60,000, $70,000 a piece, these small things, and then they can launch entire fleets up into the sky to be able to effectively monitor the entire globe almost in real time. And so what we're looking at for the near future is, whereas the data that underlies Google Earth takes approximately 2 years to complete a new picture of the entire world, we expect that within around 5 years, private satellites will be able to cover the entire globe every 20 minutes. So this is a completely different class of the types of problems that you can address, and then also a completely different regime for the big data that you need to deal with in order to make sense of all of these information. So Descartes, in order to make sense of these data, we're building a living digital atlas of the globe. And so during this talk, I want to tell you a bit about that, and then how we're using machine learning to understand the value and the information in these pictures. So we can think about this as a classic big data challenge with the 3 V's, volume, variety, and velocity. And so in this context, volume is what it usually means, the massive amount of data that we need to be able to pull in and work with. Variety in this case means the different types of data that we want to synthesize into analyses. And I'll talk about all these in more detail. And velocity here, I really mean 2 things. I mean, first, being able to access all of that data efficiently, but then also being able to analyze and scale your analysis across the globe, rather than having someone look at individual pictures. So to kind of work through those with some numbers and a bit of detail, global satellite data sets are very big. This composite that we made is comprised of 3.1 trillion pixels per band, and the Landsat satellite that took this has collected over 70 trillion pixels between 2013 and 2017. So that's comprises 320 terabytes on disk, and that's just one satellite among many. So we've processed around 10 to 12 terabytes of data, petabytes of data onto our platform at this point, and this is just going to expand exponentially. But just to give you bit of an image in your head of what that looks like, let's take one satellite, the Sentinel satellite, and take all of the picture that it's taken and print each individual band out on a 1 millimeter thick sheet of paper, stack that up, and that would form a column that's 410 kilometers tall, so from the surface of the Earth up into the thermosphere. So it's a lot of data. The data variety that we're working with comes from different types of sensors that we want to be able to work with and synthesize together. So here on the left, there are passive sensors, like normal pictures that you would take. In the middle, there are active sensors, which actually send down radiation or radar and then receive the signal and interfere it to get 3D information about the surface of the Earth. That's called synthetic aperture radar. And then there's near-infrared data that actually measures the thermal emission from sources on the ground. And then there's all kinds of other geo-relevant data, like weather, cell phones, derived products, derived mass, customer data. So we want to be able to put all of this into the cloud in a way that customers can access in an efficient way to be able to build these types of analysis algorithms. And then velocity. So thinking about how long it takes to work with these types of data, let's consider again the Sentinel satellite. So if we take 1 year of data, Sentinel satellite covers the entire Earth approximately once every 5 days. Let's now chop up the entire Earth into 512 by 512 tiles at 10-meter resolution, and then give a human analyst 10 seconds to look at each picture. That would take them 130 years to go through 1 year of satellite data for one satellite. So obviously that's silly. We're not going to do that. But that kind of illustrates the problem of the old way of thinking about satellite imagery analysis and why we need new approaches. And then also for velocity, thinking about the computation that's required to handle these types of data. So again, coming back to this composite that we created, this was made from processing over a petabyte of NASA imagery. And we did all this processing within the cloud using preemptible VMs. And by spinning up 30,000 cores, we were able to process and create this image in under 16 hours. And this also this is actually even larger than the throughput that we need for the current data sets. But it demonstrates the capability that Google Cloud will be able to scale as the data that I'm talking about continues to grow in the way that we expect. So to handle all of these data, as I mentioned at the beginning, we're building a data refinery, or a platform, to better understand our planet. And so what we want to provide is ready access to petabytes of geospatial data, and then scalable compute to back that up and be able to create automated and scalable analyses. And these are just a few of the satellite sources that we have on platform right now, and this is going to just continue to grow. So I've talked a lot about all these, all of this raw data, but what's really important is that the value lies in the information in those pictures and the decisions that you can make from that information, not in the raw pixels. So it's important for us to be able to sift through all of that data and arrive at decision points, or being able to monitor something in a supply chain, or make a decision about whether we're going to go here or go there. So being able to pull together all different types of data. So here's SAR over Tokyo, where you can see the ships coming into port. Being able to understand the changes over time. This middle image are segmented crop fields in Nebraska that were created by looking at detecting edges in images and then looking at which edges persist over time to be able to tell what fields are what. And then using machine learning, which I'll spend the second half of my talk talking about, to be able to analyze all these data at scale. And then what this gives you is really a geospatial refinery for business intelligence. So again, taking all this data, processing it, and then turning it into value and decisions that you can use. So what the platform actually looks like then is effectively a Python API for Earth, is what we like to call it. So let's say, for example, you want to gather Sentinel imagery over Taos in northern New Mexico. If you were to start from scratch trying to go directly to the satellite source, this would be quite challenging. But for us, it only takes 4 lines here: importing the package, specifying the location, doing a search over all of that giant catalog of metadata to find the Sentinel imagery over this place in 2017 between March 12th and March 20th, and then taking all of those numbers and burning them into an image or a picture that you can actually see and work with. So under the hood, what we've provided is fast access to over a petabyte of data on the platform. The search function for searching through the metadata is done with Elasticsearch, and it provides millisecond response times over all of those data. And then an automatic tiling system, so you don't have to worry about pulling together different images and making sure you register them correctly, all of this. And if you want more detail about the underlying platform, you can go back and watch Tim's talk from yesterday, IO 263. So the second half of the talk, I want to talk about the machine learning approach that we've taken to trying to understand these data and derive value from it. So I think another important change that at least the geospatial data community is going through right now is, whereas previously images were thought of as something that a human analyst could pull up on their screen and then look through and study and annotate, with this massive amount of data, as I mentioned, that's no longer sufficient. And so we should start thinking of these images and all of these data as input to computers, input to algorithms, what computers are seeing out of this, rather than what humans are seeing out of this. And it really changes how you think about the type of analysis and the type of questions you can answer. And so that's what's going to be required to automate data analysis that you can scale across the globe. And then this also encourages us to simply think differently about the types of questions that one can answer. So hopefully I can get you all thinking through this talk. So a little bit about what the input data looks like from, so now me as a computer vision engineer, I come in and I say, how am I going to create a new useful tool? So let's start with the input data. As I mentioned previously, there are several different types of images. The most common are passive sensors, where the sun is the light source. It shines, reflects off the surface of the earth, and you take a picture of that reflected light. So that's like normal CCD cameras. Then there are active sensors, which are their own light source. So like, for example, synthetic aperture radar, which sends a radar signal down, reflects it off the surface of the earth, and then receives that full wavefront, which it can measure and interfere, and then use that to reconstruct 3D models of the ground. So we collect these data, and what many of the algorithms that I'm going to be working with are supervised algorithms. And so oftentimes it'll look like image target pairs. So here, for example, on the left, I have a picture over a city of high-resolution satellite imagery. And then on the right, I have a labeled image for where all the buildings are. And so this is the type of input data that would go into training an algorithm. These data are, because the platform is in Google Cloud, it's trivial to be able to process all of these data and create these pairs directly in the cloud, and then save them to cloud storage, and then be able to access them seamlessly without having to use any local resources. For those of you who think about analyzing imagery, I just wanted to highlight a few of the similarities and differences between processing normal imagery. So many things are similar, but there are some key conceptual differences. So in particular, satellite imagery usually has a known size and scale with units. Pixels usually correspond to a specific size on the ground. In terms of data augmentation, these images are left, right, and rotationally invariant, so you can flip them all around to augment your data sets easily. One of the key differences is that oftentimes we're interested in finding things right at the limit of the resolution of the imagery, so small objects within images. Whereas in normal imagery, whether it's the cheese example that we saw from AutoML, that piece of cheese takes up almost the entire image. Here we're looking for, you saw the buildings, we're looking for those little specks. So the scale, in terms of thinking about transfer learning, the scales can be different. There are almost always confusers in the data, like clouds, haze, and shadows. So that requires a lot of pre-processing, and I'll show a little bit later of dealing with that. And then in normal imagery, there's usually 3 bands, whereas in satellite imagery, we can have an arbitrary number of bands. For example, the Sentinel satellite from Europe that I've referenced a few times has 12 bands, from the visible all the way up into thermal bands. And then a similarity that works well with working within the cloud is that these problems are generally embarrassingly parallel. You can take a full stack of images in normal image processing, or you can tile up the Earth into a stack of images and then send them off to an arbitrary number of processors to be able to run those jobs in parallel. Okay, so now we've thought a little bit about the input data. How do we want to analyze these data? Well, there's three sort of dimensions that I like to think about when thinking about satellite imagery: spatial, spectral, and temporal. So spatial is just where you are on the ground, so the 2D context of where you are on the Earth or within an image. Spectral are the different wavelengths of light that we record when we take imagery in different bands. And then temporal is for a given location, obviously. As you take pictures over time, you can see what changes. And so by combining these different aspects in different ways, we can access different types of problems. So, for example, computer vision will usually be combining spatial and spectral information, where you're trying to understand the spatial context within an image and then look for spectral signatures of different types of objects or land cover that you want to be able to find and map. And spectral and temporal can often be used to look for and monitor change. So for example, looking at crop fields over a growing season, you can see how the plants are growing and changing over time. And then obviously, many of the final solutions will be hybrid approaches that will combine everything, and I'll talk about one of those at the end. So because we have chosen to work within Google Cloud, building these ML models is a really efficient process. So we work within virtual machines on Google Cloud Platform. That allows us to easily scale the resources that we need to process images, train algorithms as needed. And then we're able to maintain environmental consistency from that development and training process all the way through to deployment by using Docker and Kubernetes. Because our data live in Google Cloud, it provides us super fast access to that giant body of data. And then for training, we can download smaller sets to VMs or work with it directly from the cloud. And then we can deploy at scale. So as I mentioned, most of these are at the deployment stage. Most of these models are in an embarrassingly parallel problem. And so we can simply spawn up an arbitrary number of processors. If I want to run a model over the world or over the United States, I can just spawn up that number of processors and get the results that much faster. And then results are saved directly to the cloud. So it makes it from research to building models to deploying those models, working within the cloud provides us an incredibly efficient environment for doing this work. Okay, so now I would like to tell you about three different, more specific machine learning approaches that we've taken and the types of problems that we've been able to access with those. So I'll dig in a little bit deeper into the machine learning side of the models we're building. So the first is object detection. For those of you who are not computer vision engineers, the basic idea of object detection is exactly what those words sound like. You want to find objects. And so, for example, here we're looking for electric substations. So you want to find that object, draw a box around it, and say, there it is. The particular implementation that we've been working with so far is called a single-shot multi-box detector, SSD. Single shot because it takes a single forward pass through the architecture. Multi-box because it uses a set of predefined boxes rather than dynamically finding those boxes. And then detector because it detects things. How it works in one slide is this algorithm, as I said, predefines a set of boxes. And then for each of those boxes, it uses a convolutional neural net to generate a set of features. And then finally predict the confidence of whether or not that box contains the object of interest. So basically, it boils this search problem down into a classification problem. So here, this is from the paper that defined this architecture. The blue box has the highest probability of being a cat, and the red box has the highest probability of being a dog. So we've taken that and modified it to work with satellite imagery, and here's an example of the results of that process. So using OpenStreetMap for the known locations of electric substations, we've been able to train this using NAPE imagery, so that's the National Agriculture Imagery Program that covers the United States. This particular data set has imagery at 60 centimeters per pixel in 4 bands, and we've trained this algorithm to be able to find all of the rest of the substations in the United States. And so that was one example, and once we have this setup with all the imagery easily accessible and the modeling framework in place, it's easy to train a wide variety of models across the industrial supply chain to be able to find these objects. So here are just 2 examples of being able to find storage tanks, be able to find boats, but you can just let your imagination run wild for what you would be able to do with this. The second class of models that we've worked with a lot is called semantic segmentation. So the basic idea with this, as opposed to object detection, where you're trying to find objects, here you're trying to say, for every pixel in an image, is that pixel part of a class or not? So in the example on the left-hand side is the high-resolution imagery, again, from NAPE, and on the right-hand side is the probability of whether or not each pixel is inside a building. So similarly, how it works here, we define a deep convolutional neural net, and convolutional neural nets are a particularly effective architecture for these types of analysis because they take into account the 2-dimensional context of an image. So when if you've ever zoomed in on Google Maps and then zoomed way out, and once you zoom all the way into pixel scales, it can be really hard to tell what you're looking at, and you actually need to zoom out and be able to see that spatial context. That's kind of conceptually what convolutional neural nets are able to capture. So we define a deep neural net architecture, in this case a UNet, and then these create a bunch of these image target pairs that I mentioned at the beginning, so in this case about 10 to 20,000 of these, and then train the model within the cloud platform. And this is what the output looks like. So these are detections from my model over LA County. So you can see the high resolution imagery on the far right-hand side. This is the raw probability map output. And then in the middle, these have now been segmented into individual buildings. And so what's especially powerful here is once we have this model, as I mentioned earlier, being able to run this over large areas. So I was able to map all the buildings in California by hitting run, going home, sleep, and then by the time I got back in the morning, we had a map of all of the buildings in California. And in principle, we can do this over the entire world. Another type of segmentation that we've been able to have success with is using neural nets to mask out clouds. As you remember at the beginning, I mentioned this is one of the pernicious problems with satellite imagery, is clouds exist, much to our bane of our existence, I would say, rather. And so by training a neural net to find clouds and cloud shadows, we can now automatically mask out these out of images and then be able to remove those parts from the analysis. And this is, this can always get better. This will be an ongoing challenge, but this has been a particularly successful approach for being able to deal with these types of non-idealities in the data. Another approach is what I've called here coarse segmentation. So this is actually basically a transfer learning approach, where we start from a ResNet 50, a pre-trained algorithm, and then we tap into one of the lower resolution feature layers, and then simply add a final classification step to say whether or not each of those coarser pixels is the type of thing, in this case windmills, that we're looking for. And so we've taken advantage of the fact that ResNet has been able to train on many images, and then with a relatively small number of examples, I think of order 1,000, a few hundred to 1,000 examples here, we've been able to train an algorithm that can find and map windmills. So this has been done across the United States and across India. And then finally, it's still semantic segmentation, but a bit of a simpler model is simply pixel classification. So taking that, remember I mentioned the spectral information within each pixel, what you see in different bands, and then feeding that into a random forest classifier, and then just training it with a bunch of data to say whether or not each pixel is land or water. So this is in the Mekong Delta, and you can see it clearly gets the oceans and the rivers, and then there are a lot of rice paddies in these areas, so that's kind of what the speckly pattern that you see throughout the Mekong Delta is here. A third type, and this is fairly different, is what we've called visual search. So I'll demo this in just a second, but the idea is that this is a website that you can go to. You can click anywhere, either in the United States or on the Earth, and it will simply find other places that are visually similar. So let me go into a little bit of detail on what's going on under the hood, and then we can play around with this a little bit. So what's going on is that we've taken the entire data set, so the entire globe, we've chopped it up into lots of little pieces, and then we feed each of those pieces to a convolutional neural net to produce a set of features, and then we simply search for nearest neighbors of features. So in even more detail than that, we started from a customized ResNet 50. So started from ResNet 50 using all of that, the training that had gone into producing that model. And then remember I mentioned that oftentimes you're looking for small things in images that are different from normal image processing. So we fine-tuned trained that with the OpenStreetMap data set, and then also some unsupervised auto-encoding to be able to produce a useful set of features. We then encourage those features to either be 0 or 1, so binarize that set of features. And the result of that process is that for each tile, we get 512 binarized bits, 0, 1. Then we can simply search for which sets of features are close to each other, and using a Hamming distance. And so we define that distance using a Hamming distance, and then we search for it using an approximate hash-based nearest neighbor search. And so the result, if I can switch over to the other laptop, let's see if this, oh yeah. Okay, so this is now the website running live. And so any of you can go to this at search.descarteslabs.com. So first let's play around with the United States. So this is this National Agriculture Imagery Program data set that I've mentioned a few times. And so highlighted a few popular searches, but let's click on wind turbines. So what this has done is I've grabbed this tile, and then, like I said, we've already indexed the entire United States into these 512-bit long feature vectors, and it simply searches for other ones that are similar. So it's pulled up a whole suite of different wind turbines all over the country. So some here in the Midwest, some in the Northeast. And this is not a specifically trained model. I didn't have to I didn't have to know anything about wind turbines to be able to create this. This is just simply searching for visual similarity. Another one that I thought was kind of neat was the solar farms. So looks like this is a solar farm maybe in Arizona or New Mexico. And so, yeah, so click on that, and solar farms look very similar. So this does quite well at picking up solar farm installations. So let's then also look at the entire Earth. So we've done this with the Landsat data set as well. And so, same idea, being able to index the entire globe. So pivot irrigation are a very unique signature. So I can click on that, and all of a sudden I can see pivot irrigation in Australia, all over Africa, the sub-Saharan, in the United States, down in South America. And so it's a very powerful tool to be able to effectively search the entire globe for things. So you can go to this today and say, I want to look for railway stations that look similar to the one near my house. Let's click on that and see where else they are around the world. And so this is this incredibly fast search, and so you can see how quickly we're able to zoom around. This is all enabled by having the platform built within the cloud. So if I can go back to my talk slides. Perfect. So with those two approaches, we basically have a two-stage approach to performing searches when we say we want to try to find some type of thing. Because of the capabilities of the geovisual search, we can do a low capacity, quick search for things like the wind turbines. Just click on that, or build out a small model and say, let's just try to find roughly where some wind turbines are and differentiate them from cornfields or forests or whatever. And then if that's enough for your particular solution, super cheap, super fast and easy, you're done. No work. Then obviously many solutions will require much higher precision, so like mapping out buildings, for example, wouldn't work with that. And so then we can develop a higher capacity model that takes more time and effort. And so that's what the examples I showed with buildings or wind turbines or power substations. And then, of course, the last type of models I want to talk a little bit about are hybrid models, and an example of something we've done that sort of pulls all of these pieces together. And so what this is one of the original models that Descartes Labs produced, which is the corn forecasting model. So the goal is to be able to forecast corn production for the United States. So first, as I mentioned earlier, using the temporal information, we can segment out where different fields are and what those field types are. So how this actually works underneath is because we have time series imagery over the United States, we can just use normal image processing to find the edges, use an edge detection within those images, and then we can look at which edges persist over time and use that as a way to segment out field boundaries. Then once we have those field boundaries, it becomes a classification problem. So taking into account the spectral and the spatial context information, we can classify those fields. Here, these are either corn or soy, corn yellow and soy in green. And what you're actually seeing here is the field classification released by the US Department of Agriculture with a lot of measurements on the ground. And what you see here is what Descartes released 6 months ahead of time. So what you should say is, hey, look, those look pretty much the same. And they should, because the US Department of Agriculture accuracy is quite good. The key is that we were able to do this in effectively real time rather than having to wait 6 months. And then the final step of that model is a regression problem. So saying we have historical data, we know how much corn was produced in previous years, so let's run this model and fit to a model to predict how much corn can be produced. And so you pull all of those pieces together, and what the graph on the right is showing is the y-axis is the uncertainty on how well you have predicted corn. So small uncertainty is good, so down is good. You can see, and then as a function of time, and so you can see as you go to the far edge of the graph, so you extend to time, they approach the same accuracy, but the blue Descartes Labs points got there way earlier. And so this gives businesses and customers like real actionable insight that they can turn into real value and money. So that's wrapping that up. If any of you are interested in building models or if this brings up ideas, feel free to come up and talk to me. There's information on our website, and then you can email either of these email addresses. And so I'd love to talk to you more about what types of problems you might be able to approach with these types of data, or more questions about how we've been able to build out all of this infrastructure and our platform using Google Cloud. So with that, thank you all for coming.